Hi, how are you? Hey. Yeah, I'm tired too. I will just lie down this way, it's nice. Okay, so. Computers being computers. So, I will talk about Rust for a bit. Me, I'm Geoffroy Couprie. I'm a French guy. I work at Clever Cloud. We're a platform as a service hosting company. Like the thing where you do a git push and it goes to production and it runs, it does not crash, or if it crashes, we restart, and it auto scales and everything, and it's great. Come talk to me about it afterwards. All right. So first, I have a small question for the audience. Did anyone do C development at some point in your life? Yeah. Do you still do? Yeah, yeah, I guess so. That's the same for me. Like I was a C developer at heart, and I really liked C because you can do a lot of low-level stuff. But at some point, I was just so frightened that I will put something in production and it will be exploited, and it will just plain crash or eat the memory, and it was very distressing for me. But there's still good reason to write C code. Like speed, it's still easy to write fast code in C. You can really micromanage the memory, and it's portable. You can write code for almost any platform available under the sun. But why should we avoid C? Like, we have all seen that kind of thing in various operating systems, even your phone, your watch, everything, it crashes. There are vulnerabilities, like people will just take over your whole program. Like it's a pain. It's a pain to compile. It's a pain to write correctly. And if you tried to link C code to any other language, you've seen that like FFI is a complete mess. So, hi, let's do some Rust. What's Rust? Rust is a language that came from Mozilla. Well, they had an issue. They were writing a browser that's called Firefox. I don't know if you heard about it. It's like this huge chunk of C++, like so huge that they had to build a complete web app just to browse the code. Because if you grab the code from Firefox, it will take so much time that you won't get any work done. So you have this web interface when you can click some part of the code and get to the definition and everything. Otherwise, it's impossible. And they had lots of issues. And when Graydon Hall, one of their developers, said, "Hey, I've been toying with this language called Rust in my free time. It's memory safe. Kind of nice features." Mozilla started to sponsor the stuff. And this is a slide. It's a slide that comes up at every Rust talk in the Rust conferences. Like, we want to have a language that's fast, that's reliable, and that's productive. It's not a joke that we will get all three. It's we want them. If it's not available, we will make sure we will get that. So, how does it work? The idea is you will have like high-level tools, but for low-level programming, and a compiler that will do a lot of work for you. So, in the design, it's an object language without classes. Let's not get into the debate again. There are traits. If you've seen that, I will show afterwards. Everything is immutable by default because it's a lot easier for the compiler to just reason about the code. And if you think about it, like most of the time, the data you will use will be immutable. No garbage collection. It's a pretty funny part of the language. Like at some point in the development of the language, they had the idea that there would be garbage collection. And once they said, okay, so the compiler is now smart enough to manage the memory, so we don't need garbage collection, we will just remove that from the language. And it's the idea of the zero-cost abstraction. A lot of checks are done by the compiler at compile time, but will not result in code at runtime that will do the checks. Like, you make sure that the allocation and deallocation of memory are done here and there, like you would do in C. In C, you do a malloc, and you do free. In C++, you do a new or delete or auto pointer shared stuff whatever. In Rust, you let the compiler take care of that. It's smart enough to know when to allocate or deallocate memory. But you don't see a cost of checking everywhere if a pointer is null of everything. So in the way it's written, it's quite straightforward. Here's a function, yeah. We have structs. I say we have kind of object-like thing, everything like the structs, enums, and everything. This is the basic storage of data. We have enums. So this the option type or the either, if you've seen that in other languages like the recent Java or Scala. And there's pattern matching, which is like a central way to write code in Rust. Basically, I almost forgot to put that in the slide because it got just so basic for me that I just yeah, it's there. I talk about the traits. So instead of having inheritance between classes and objects and stuff, you define this kind of interfaces and you implement them for this struct or this enum and whatever. Here we have just the trait to get the area that returns a float on 64 bits. And like, okay, we implement that for a circle. It's quite straightforward to do that. The syntax can take a bit of time to get used to, but basically it has inspirations from C, from Java, from ML, from a lot of languages. Another thing, there are closures. A great thing with closures is like most of the time now they are not even allocated on the heap. Those are closures that are generated statically at compile time. So it's just like calling another function. It's not something that will have a runtime cost. And the big feature of the compiler, the borrow checker. This is the thing that will tell you, okay, in this part of the code, you do something with the data, with the memory that you should not do. And it's really hard to get in front of that part of the compiler that will just say, okay, this code that you've written in a lot of other languages that you put in production, I'm telling you now, you made a mistake. And like, a lot of time there are people coming to the Rust IRC channel and saying, okay, so the compiler said that this is wrong, and I know it's right, I have been running that code, and I know it works in other languages. And then someone just raise their hand and say, hey, yeah, but there's this 1 in a million case, where 1 in a million time case, where it will just completely burn your computer. So there's been a lot of work, a lot of check are done at compile time to help you. So here it's a simple one, like you have a function called foo, which will take a reference to a vec as argument. The reference is the ampersand stuff. And push, you try to add something to the vec, but hey, it's not marked mutable. Otherwise, it would have been ampersand mute. So it's not mutable, so you cannot modify it. And a lot of things like that are there. Like another one, when you try to modify something while somebody else has a reference to it. Like when you have a mutable reference to some code, nobody else can read it because you don't know what will happen if someone reads the code while you're modifying it. So like millions of checks to make sure that your code runs right. But at first, it's a bit hard to write code because you're not used to think about this. So it's getting there. Like a lot of the checks now, the compiler is getting smarter and is able to infer what you want and will not annoy you with the references and stuff if it knows it can make it safer. So it's a bit young yet. It will take a lot of time to get something that's usable for everybody, but it's getting there. So we use Rust at Clever Cloud a lot. Like I've been evangelizing using Rust for like 2 years something, and saying, okay, this is a great language. I have to rebuild the compiler once every 2 weeks. The language is changing all the time, but I have no crash. It's fun to use. It's easy to maintain. It's easy to refactor. And like we have lots of tools that are now being rewritten in Rust, Like, I'm not even the first one to build some Rust at Clever Cloud. Some things have been there like for months now. Even the CEO is shipping this week a project for that. And we can put web apps on our platform with like 5 commands. You install the tools, you create your Rust application, you push it, it will compile and run, and it will be there forever. So this is a great language, and I really like it. Maybe you've not seen how I like that language, but whatever. Why would you use Rust? So we've seen that C is interesting, it's low level, but it crashes. Rust will do the memory work for you. So it will prevent the vulnerabilities you have to think about when you're in C. Like in C, you have to think all the time, where is that thing deallocated? I am really calling a pointer that's valid. Is there something behind that pointer? I don't know. You don't know what can happen. And there's a nice perk of Rust is like the build system is very cool. You don't have to mess with the auto tools and stuff. We will switch. I don't know if you've tried to do anything with makefile and auto tools and autoconf and whatever, and it's a specific kind of fun. Yeah, you can see the pain from in some people there. So, well, the thing is, it can pass itself as C. Like you can take a dynamic library in C or C++, and you can write one in Rust that will appear just the same. Like the same function are exported, you can do the same code and whatever, and it will be loaded in another program without any issues. One of my big examples is that I made a parser for FLV files, so the Flash video, and I made a plugin to parse Flash video files for VLC. And there's no C code in that plugin, it's just you put there in VLC, VLC loads it, it parses the file, gets the video, it works. It's doable in Rust to just replace some C code. It's not necessarily easy, but it's doable. You can do some native extensions for languages like Python, Ruby, Node, Haskell, and everything. You can make some WebAssembly stuff. I still don't know if there's a good use case, but I want to see it used because it's very fun to like compile to JavaScript. And as we will see, in Java, it's the same as for C. You can access it with Genui and GNA. So why would we use a language like Rust to write those native extensions? Because sometimes, like you're in Ruby, you want to have like fast code. You will write C, and you don't want to spend 3 months to get used to Rust, while you can just do a big mess in C. Well, the difference is in one thing. Okay, it's hard to get right, but once it builds, basically it works, and you will not make as many errors as in C. Like if you try to put some C code in production, you will have lots of issues. So it's a serious contender to replace some C. Why would we replace some Java? Because like a lot of us are doing some Java here. So it's very portable. Like you can build for almost any platform. All of the ones that are supported by LLVM, basically. It's very low footprint. Does not use much CPU or RAM or whatever. There's no runtime. It's like C code. It's very easy to write low-level code, like in embed assembly stuff. You can write an operating system in Rust. A lot of people have done it. And like, as I said, no garbage collection. So maybe it's not enough to convince you, but like I have other reasons to not do some Java and prefer to do some C. So we have good lambdas, the option types were right from the start, tuples, enums, unsigned integers, like, yeah, and whatever. So, no, I don't want to start a flame war, but like, different languages, different needs. I like Rust. So now let's do something. What I want to show you now is something that I extracted from a client project. We had an iOS app and an Android app that should communicate with some kind of crypto protocol and maybe communicate with the server side as well. And basically the idea build 2 different implementations in Objective-C and Java, and maybe one in Python. And all of them have different bugs. And whenever you have like the smallest mistake in crypto code, then it will be complete garbage everywhere. You cannot see what happens. So the idea was, okay, let's make one library for everything that will be coherent with itself. And we will use that and make bindings for all of the platforms. And I said, wait, we won't do that in C. Like, it's 2016, like we can now do something in Rust, it's cool. So is it doable to do that, to write code for all of those platforms? Well, I don't know if you remember that motto from Java a few years back. Well, Rust, you will build once, you build for all of the platforms. It will take some time. Like, I spent hours building for all of the CPUs for iOS. It's a complete mess, but yeah, we can do that. So I cannot show you the code for the crypto protocol stuff, but I have another example I got. So we'll build an inverted index. An inverted index is a small data structure that's used in search engines. Basically, it's a very naive algorithm. The idea is that you will take a whole bunch of text and see which word appears in which text, and you will when you can get for a word, okay, it's in this text, this one, and this one. Inverted index. Yeah. The algorithm is very simple. You take the ID of the text, and you get a hash map of word set of IDs, and then you just have to get the set for one word. So yeah, with this small phrase, it's very easy to do. And there are just small things you have to make sure that you normalize the words, like if there's some punctuation, if there are some uppercase letters or whatever. It's where a lot of the issues are. Like, I don't know, there's a word that's plural, but you want to only store the singular one. It's where you have to do a lot of intelligent work, but let's do something very naive for now, because like I don't have much time. So a small thing, like if you want to search for a few words, you search for one word and then the other, and you get the intersection of both. It's very, very naive as algorithm, but whatever, it's a good test case. So how do we model that in Java? The index is a hash map of a word in string, and a hash set of indexes, and the integers are just the IDs of my data, of my text. We have 3 functions: one to insert something with the ID and the string, and it will just explode the text and add the words to the index. One to get the set for one word, and one to get a set for a string. And I should have made hash set for the search string, but whatever. So the insertion in Java, we split the text, remove all of the white space, and for each word we will try to normalize. So we put the word to lowercase and we remove punctuation. It's a very naive normalization, but whatever. We try to get a set if it already exists. We put that in that set, or we create a new one, and afterwards it's done. It's already there. To get the index for one word, it's quite easy. Just call the hash map with your word, and you get the set. To search a string, there's a bit more work, where you must get the first set in the list, and then you do the intersection of all of the sets afterwards with retain all. So it's like, I don't know, 20 lines of code to do that, to do a very, very, very stupid search engine in a small Java Android application. So yeah, we need some data. I thought about it. I wanted to import some Wikipedia stuff, but I would have to parse it, and it's a bit annoying. So There's a really nice API that's been done by Nicola, which is right there, to get all of the data for Devox, all of the Devoxes, and yeah, you get the data for each day, each talk, and everything. So from there, I extract the speakers, the list of speakers for one talk, and the titles and the summary, and I will just put the title and summary in the index. So there's an Android application. I will give you the code afterwards. It's easy to see, but like the interface is just this this search box. You put the word, you get the list of talks. It's something that's pretty straightforward to do. And like as we've seen, it's easy to write that code in Java. But now let's imagine, okay, maybe we want to have that search engine portable, like we want to use the same one on iOS. We want to integrate that in a Ruby application. We want to run that on a microcontroller. I don't care. I needed a good excuse to do some Rust. So let's do some Rust. Yeah. So the idea, stop looking at the GIF. The idea is we write a Rust library with a C interface, and we will load that with GNA. I'll talk about that afterwards. And once we get something that can be loaded in the Android application, we can start to write the index code and start to rewrite stuff from Java to Rust. So first, we need some test code. So when you want to do a native extension for your language, the thing that will be the biggest issue, or even when you want to do Rust with anything else, is the build system. Basically, you want to make sure that it will compile fine. So you don't start writing the whole code right away. You first start with a simple example. So we have a function that can add two integers, not unsigned integers, because hey. And we will try to access that from Java. We have two solutions, basically. Genui, which is something that's very verbose. The idea is that you will load the library in Java, and the C code must expose functions that match the package, class, method way to do Java. And GNA is a bit more easy to use, but there's a kind of overhead. But GNA is basically you declare your C function in the Java, and you can call it that right away. So in GNI, this is how I write my Rust function. So it's a bit painful to do. Like I've done it for the other client project because I really didn't like GNA. For that, I wanted to like micromanage my type in the FFI. I wanted to make sure that I got everything I wanted. But basically, you emulate the method calls and everything from Java. Like you will take the GRE reference, and you can ask it to get a reference to a class. Then you ask the class to get a reference to one of the methods, and you call the method with one of the arguments is the object, and it's extremely verbose to use, and you have to declare your function like Java conf or whatever until you get to the class and the method. In GNA, it's a bit easier. You can declare that like any C function, and it will work correctly. On the Java side, if you write GNI, yeah, I'm in the package. I declared the same in Rust. So Java com in Rust with Rust and the Rust class and add. And now I have this function add that's there and declared as a native function. GNA, you just declare an add function there, and it will find where it is in the library. Basically, the idea is that GNA needs two jars, or only one of them. I don't remember exactly what was the difference. One GNI wrapper and we'll do the calls for you. There's a small overhead on every call, but it's not that big. And so for our build system, we'll do something easy. But here are the steps. We build with Cargo, which is the package manager for Rust. Cargo build, we set the target, which is ARM, Linux, Android, EABI, to say, okay, we will build something for an ARM Android. Rust now supports building for a lot of platforms, and like all of the iOS CPUs are supported as well. And we get the libindex file, which is a dynamic library. And in our Android code, we put the jars in libs, and in the Genui libs folder, we put the Genui dispatch and our library. Okay. From there, we get something that builds, that will launch, that will be maybe able to load the library. We can do something more than adding some integers now. So let's write the index. So if you remember, in Java, where was that? And there. 3 functions: insert, search word, search string. And we have a hash map of string and hash set of integers. So in Rust, yeah, it's there. So we have a hash map of string to a hash set of integers. It's the same data structure. We have the insert function taking an ID, and the search word taking a word and returning an option of hash set, because maybe we don't find the word we're looking for. And the search for a string, search function. I made that as methods on the index structure. So as you can see, for the search and the search word, the first argument is &self. It's a reference, an immutable reference to self, but the insert takes an &mut, and that's saying basically, I want to be able to mutate the index. This is pretty powerful because you can have a lot of methods on one structure, on one object, and depending on who is using the code, they may have a mutable reference or they may not have one. So you can pass the index to someone after having created it, and you pass an immutable reference, and you can be sure that they won't be able to mutate anything because it's guaranteed by the functions. It's pretty great to have that, to have the mutability that's explicit. If you written C, you may have seen like everything is mutable by default, and when you want to make something immutable, you have to put a const. So you have to explicitly make it safer. In Rust, you have to explicitly put the mut. So it's easy to grep for that. And the same way, there are a lot of things like checking for error codes and everything. We have an option as return for search word. In C, if you have like something that will return either a pointer to something or no value, it will return null or no value. And maybe you won't check the pointer, and it's implicit. You implicitly decide to not check the pointer, and you cannot see the error checking code. In Rust, when you want to ignore the error code and get the value inside the option and not caring whether it's null or not, you will add unwrap, and you grep for that because unwrap will create a panic, will crash your program if the value is not there. And you can see explicitly that there you decided to make something that's unsafe. So it's a pretty powerful way to write code because basically all of the unsafe patterns are very, very easy to see in the code. And like right now, whenever I see my Rust code crashing, it's, oh yeah, I unwrapped something there and I made a bet and I lost. Yeah, basically you still cannot prevent the developer from shooting themselves in the foot if they really, really want that. But you can make it a bit harder. So let's write the insert function. There's a bit more code now that what we had before. So the first 3 lines, it's basically there's the regular expressions library in Rust. It can precompile the regex, and lazy static is something that will create a value the first time you access it, and then it's not then you cannot mutate it. Since my regex to remove punctuation is used only once, is generated once and used everywhere afterwards, I can just generate it at that point. And yeah, there's an unwrap. I made the bet there, but it seems it does not crash. So if I want to insert code, I call split whitespace on data. Data is my string. Split whitespace generates an iterator, and I can do a for each stuff. So for word in the list of words split by whitespace, I will normalize it. So I replace with the regex all the punctuation by nothing, and I put 2 lowercase, and I get my word. I check if my index contains the key, contains the words, and then it gets a little bit more complex than the Java code. So the ID, we have the index, which is in self in the structure. So self.index .getMut. I want to get a mutable reference to the hash set that's that I can get from that word. So I know the hash set exists. I check that it's contained there. And then when I get the hash set, I do a map. GetMut returns an option. I do a map on that, so I get the hash set. And then I insert my ID. So this is something that I wrote, like just, okay, I want to do that. Now the compiler will tell me, so you need to have a mut there, something, and then you need to have an ampersand. Basically, I don't think much about the way I write code. I just let the compiler tell me, you made a mistake there. So in the end, it makes something that's quite small, but it then can be a bit harder to read. If it's not there, we create a new hash set, a mutable one. We do let mut instead of just let. We insert the ID, and then we insert in the index this hash set at the key word. But it's basically the same algorithm as the Java side. So now, we won't do the rest of the algorithm right now. We try to call that from Java. So this is where there's the most work when you try to link some Rust to some other language or rewrite some code at the interface between both of them. Basically, we have an index that's a Rust object. It's not managed by the Java garbage collector. It will be managed by Rust. But once you give something to the language that's calling Rust, basically the compiler says, okay, yeah, but it's not mine anymore. And that's the idea of box. If I don't put my index in a box, in index create, if I don't put it in the box, Rust will say, okay, I still own that thing, so I will just delete it at the end of the call. But you put it in the box, so you tell the compiler, okay, I'll give the ownership of that thing to the code that calls me, and I return the box of index. The second function, well, you get the box, but you don't get a reference to the box, to the index or whatever. You get the box itself, so you own it. And the compiler will say, okay, yeah, well, you do nothing in your function, but I own that box, and it's not used afterwards, so I will just remove it at the end of 3. It's a pretty fun way to just delete data. In the insert, so we get a reference, a mutable reference to the index. We need to have it mutable. We need the ID, and we get the text as a C string, because that's how GNA works. So basically, it's a list of bytes terminated by a null char. So first, we have to do an unsafe manipulation. Basically, unsafe is a way to tell the compiler, okay, I will do something with the memory that you don't like, but if I can guarantee you that inside that part of the code, I did not make any big mistake, guarantee that the rest of the code will be safe. Because sometimes when you do interface with external code, there are pointer manipulation and things like that you have to do. Like, I could have added some code to check that the index is not null. Because I don't know, I could have obtained a null reference from the Java code. So we create a CSTR, which is a C string in Rust, from the pointer. We get a slice. A slice in Rust is a structure that contains basically a pointer to something and a length. Then we call the str from UTF-8 function, which will check that the data is made of valid UTF-8 characters. And if it's all right, it will return an OKey of something. And then I know it's a valid string, and I can insert that in my index. And I add another method to just see like how many words I have and test that with Java I get the same data. It's for my index, I get the number of keys and return that as an int. So as we've seen, Genui makes it easy to call the code and just declare the functions like they would be done in C. There's something you can do with Genui is exposing the struct itself. It can understand C structs. So I could have accessed like the internal things like if you remember the point structure with X and Y and the coordinates and everything, I could have used that from Java. But the Rust hash maps and everything are pretty opaque for Java. So I would just say, okay, I give you a pointer and you call my functions with that pointer. You don't try to do something else. And now I can test the code. See if both of them work the same way. So for the Java side, I create a new index. And for all the talks, I insert the title and summary. For Rust, you need to have the instance. So if you see, the instance is a reference to the library, and that's mapping to the class we have there. So I call that instance, which is a Rust, and I call the method it has, the static methods, with the Rust index that I got before. And it's the same way to call it. It's a bit verbose, but you can very easily make a big wrapper around the Rust library. And then there's an asset, so you have to take my word for it, but we get like the exact same number of words, of keys, so it's great. But we need more tests. Like, I'm trying to write some code from Java to Rust. I want to make sure that I have the same feature, that I work the same way, that I don't introduce bugs. Because what I want is like portability, compatibility, interoperability. I want something that works exactly like the way I need. So I need to add the other features. If you know that there's a keyword you can check, you can search for, that's called golden master testing. It's a very, very great way to plan the rewrite of something, or basically you will test the old code and new code on the same data and check the result and do that like for months to make sure that the results are consistent. We won't do that today because no time. So let's implement the search. It's like the Java side. You have a hash map. You give the word to the hash map. You get the data. Okay. It's easy enough. And I said you return an option. The real annoying part is this one, because I have to make it safe, and Rust can fight me a bit on that. But let's see. So first we do a split white space. We get an iterator. Now it's the same as Java. We want to get the first hash set. We cannot do like this big for all hash set in the stuff for all the words, because I need to do the intersection of the hash sets. I could work through the whole iterator if I made a union of everything, but no, I have to get the first. why did I choose that kind of use case? Well, so I get the first word. I normalize the word. I replace the punctuation with the regex we had before. I make it lowercase. And then I search the word and I get an option of hash set. So in first, we got the first element we called next. But next gives us an option as well, because maybe there's nothing in the string. So what we get in first is an option of hash set. Because it's annoying to have like multiple calls that can fail, so you have to handle the case correctly. But in this case, it's interesting. We can just care for one case, which is like it's something of something containing a hash set. And that's where I get the if-let stuff. Basically, in Rust, everything is an expression. So you can do something equals if stuff else something. And this is valid. So I want a hash set. I get res, which is a hash set of I32. And if first is a sum of hash set, I clone it, because the hash set I got from the index is a reference to the one. You see how it's still a bit harder than something like Java. Like in Java, you just return the hash set and everything because it's garbage collected. So you know the reference will disappear at some point and it will be deallocated when needed. But in Rust, no. If I return a reference, I have to use a reference. But the case I want to have my set containing something. So if there was no first word on in the string, or if the word was not there in the hash map, I return an empty set, and whatever happens afterwards, the intersection will be empty. Then this is a fold. You give it a first parameter and an operation that takes one parameter of that type and then the next one in the list. And so I iterate on the list and get the words. For each word, I normalize it, and I get I call the index with that word. So index.get.word gives me an option of hash set. I map on that option, so if there's something in the option, I get an h in a hash set, and I do h.intersection with my first parameter, my accumulator set, and then I clone this and I return that. And if there was nothing, I do an undrop or, and I return a new hash set. So you will have to take my word for it that it's actually pretty easy to write. And kind of easy to read if you used to Rust. Basically, when I wrote that, I did not know like who was returning which type or whatever. I just say, okay, like you see the hash set of I32 stuff. I put that to say, okay, this is the type I want to have there. And I write the code on the other side of the equal sign. And then I let the compiler tell me, yeah, but there you did that and it's not the same type. Like you got a reference to a hash set and you want a hash set. And it's the same thing in the end in the lower part. So it's a bit harder to write, but in that case, like we have some code that's still manageable. Now, there's an issue I have there is that the hash set of I32, it's a Rust type, and it's not one of the ones that are easily mapped by GNA. So I have to have a way to return a set of integers to Java. So how do I do that? I make a new type. That's basically an array of I32 stuff. And I make the methods for that. So one to get the number of elements, one to get one element somewhere, and one to free the result. You can see that I made an unwrap there. it was to punish myself if I made the mistake to make an out-of-bound access on my result. Basically, it's hard to iterate on things that came from a native code. But I could have made like some safer wrapper. So now, if I want to use that, I make my external function, the one I give to Java, and say, okay, so you want to search that text. So the first line in the function, I get a slice from there, from the text. Then I convert that to a text that can be empty. I use from UTF-8, but instead of matching on that, I say I take the result or I replace that with an empty string. I search the result. And then I create a vec from the hash set by iterating on it. And it's cloned, so I will own the data. And then I wrap that in a search result that I wrap in a box, and I give that to the Java code. It's pretty verbose to do that, but basically, most of the time, you don't iterate on much stuff coming from native code. You try to just push as much stuff on the native side as possible. So on the Java side, you have the search function. You have the search result count, free, get, and whatever. So it's still pretty easy to declare. And the code to search everything is kind of the same. So we get the set of integers for the Java code with search string. We get a pointer to a search result from the Rust code. And then I convert that to a Java hash set. And I try to compare them, like how many entries can we get, like if I search for Java. So let's see. Okay, it's all right. No, they don't get the same result. So what happened? It turns out like I had a bug in the Java implementation that did not appear in the Rust code. Basically, for some of the talks, there was Java exclamation mark or something like that at the end of the line, and then line return and whatever, and then other words, and the Java code I had written was not taking that, so I still suck at Java regex. But I'm pretty good at Rust now, I think. Well, so it was a bit hard to do. It's always a bit hard to write native code, but now we have a working implementation, and I could use that same C interface to call that from Objective-C. Because it's some code that's easy to call from Objective-C. Objective-C is just basically C with the bad parts of Smalltalk. I really love Smalltalk, but like I can't bear Objective-C. Whatever. But still, I have another example I will be able to show you afterwards, where basically you can call from Objective-C, and you can even package a Rust code in a pod. They have the pod file stuff, which is a kind of packaging, and they have like a new one every 2 years in the iOS community, and it's doable in Rust. So there may be a question that I have avoided for the whole talk, because I did not want to get in there. It's like, yeah, but Java is fast enough, and we don't need to do some C or Rust code. So, and I agree, like Java is fast enough. But let's see. Hey. Yeah, so don't take that too. Yeah, it's just naive code on both ends, and like turns out like writing code fast and naive was easier for Rust. If you really don't like what I did, come and get me. I still like to see people do micro benchmarks. So, in the end, there's still a bit of a learning curve in Rust. It still takes some time, but the compiler team is really committed to make it easier and easier to use. Like a lot of cases where the compiler is telling you that you did something wrong, they will be able to understand what you mean and generate the correct code instead of just telling you you did something wrong. You have to make sure that the compiler is helping you. Like, if you go into the language and say, okay, yeah, it's annoying because it tells me that I write the wrong code. No, the compiler is there to make sure that you will not make too many mistakes. It's like pair programming with a robot. The robot tries to be as polite as it can, but like if you do the smallest mistake, it will see it and it will tell you. It's very explicit. So it's portable. Like, I think I could use my implementation of a bad search engine on almost every platform. I think I post that to some PHP or Ruby conferences. It should be good to have the same implementation. And FFI is kind of easy. It's harder on the Rust side, even more if you do Genui, but basically most of the code on the Java side will be easy to write, which is good because most of the time you want to make sure that the user of the library will have the best time ever. So in the end, if you want to take a look at the code, it's there on GitHub. The slides are also available. There's also a link on the GitHub one to the iOS and Android version of the code. We have lots of stickers for Clever Cloud if you want. There's the Hosting Powers one and a lot of very nice one. And if you have any questions or anything, I'd like to hear about them. Otherwise, thanks. We have like something like 9 minutes if you have questions. Or we can just look at GIFs for a long time. Yeah? Yeah.
In terms of API, we've seen the collection API. What do we get out of the box?
So the question is, in terms of API, what do we get out of the box for the standard library?
Like the collection one, what do you have?
Connection one?
Collections.
Yeah, in collections in Rust. Rust is not a battery included language. Like, a lot of things are still left to the community because they did not want to fix everybody on one implementation on everything. But the collection, like, we have the vec, the hash map, the hash set, we have the trees, lots and lots of ways to iterate on data. And basically the community had a lot of fun writing their own collection. Like, there's a kind of array that's stack allocated, but if it gets larger than some size, it's now a heap allocated array. Like, there are a lot of things you can do with the collection in Rust. But most of the standard library is very, very small because it's left to the community. Any other questions? I can show you the iOS side. I still have 7 minutes. Yeah, I think it's that one. Maybe I can. Oh no, okay. I know what I'll do. So this is another example where I have the iOS code with a small library. So no, it's not that one. It's let me check. No, it was in the example. Yeah. Okay, yeah. So in my class, I think it was somewhere there. No. Where did I put that code? Well, whatever. I can show you the Genui side. I made one library, and then I made another library, which is calling the first one, and making the Genui wrappers. And this is the one I use on Android. Maybe it's a bit small. Well, okay. So yeah, it's pretty verbose. I really don't like the way it's done, but yeah, it was easy enough to do it manually. And like for the the Rust side, basically, it's C code. It returned some C code. It was another example to prefix strings and stuff. And this is something that can be called directly from Python or from Objective-C or whatever. There are people that are doing like some libraries to make Ruby gems and Python extensions that are very well connected to the language. Like you could get an object from Ruby and Rust would understand the garbage collection from Ruby. This is pretty awesome stuff that people have been doing. Any other questions? All right, thanks. Don't forget to take some stickers.